All right, guys, here we go. So, very, very, very few promises on the AP test, right? They're not terribly forthcoming with chemistry teachers about what's going to be on the AP test. So guys, anytime we grab a hold of something that we are assured of, I got to close this because my lab's going to fill up with people. They give us an assurance of something on the AP test. That's something that's valuable to us, right? Well, what you're going to learn today will in some form be on the AP test. This is a new way of thinking about equilibria. We're going to be doing some ice boxing because you committed to me that you were going to look at the first couple sections of chapter 17. You may have read over this, even if you didn't process it and put something on paper. You may have looked over this and gone, whoa, right? So guys, let me tell you about whoa. Did I ever tell you about my high school chemistry experiences? So my high school chemistry teacher, remember this was 1987. My high school chemistry teacher, Gary Cathan, every day it was a polyester leisure suit and a tie that was about this wide. It was like he never quite let go of the disco era, but an amazing teacher. And my sophomore year, 1986, I found that I just really enjoyed chemistry. And guys, this was a high school that didn't have an AP program. We did not struggle as students with all the pressures that you guys currently struggle with to graduate from high school with an associate's degree and so many AP credits that you enter the university as a junior and all this other crap that you guys have to put up with, which frankly I'm finding is abusive because now my son's going through this as a high school student. Anyway, sorry, that was wildly political. But guys, we didn't deal with any of that. We went to high school and we learned, and then we went to college and we learned, and we were okay. So with all of that said, there was no AP program. So at the end of my sophomore year, I'd taken chemistry and there was nothing else to do. So me and a couple of my friends in high school went to Mr. Cathan and we said, Mr. Cathan, we're interested in chemistry. Is there something more that we could do? Is there an advanced chemistry class? Not AP, because that didn't exist for us, but is there something else? And he said, no. And we said, come on. And he said, all right, I'll tell you what. Sign up to be my TAs during my prep period, and I will create an advanced chemistry class for you. Pretty generous of the guy. So anyway, he created an advanced chemistry class for 4 of us. But you can imagine what happened. He got busy throughout the year, and basically what it became was self-taught second-year chemistry. He gave us a college chemistry text. He said, solve all the questions at the end of each chapter, and when you're done, keep going. And every now and then he made himself available for questions. We never did labs. It was all just read the book. And frankly, it slowly became just, he was so completely unengaged because he was busy. But we did pretty well with it. Frankly, we learned from each other, we muddled through, and it was kind of interesting in a weird sort of way. Until we hit this. This is where we gave up. Guys, this actually happened also in February of my junior year. We got to the common ion effect, and as you may know from looking over chapter 17, buffers. And we couldn't figure it out on our own, and Mr. Cathan didn't have time to explain it to us. And frankly, this is where we gave up, Cathan gave up, the class came crashing down, and frankly, he gave us A's for 3rd and 4th quarter simply because he felt guilty because he didn't have time to work with us. So, guys, left to our own devices, this is not something that I understood. Frankly, when I got to college, university professors who were notoriously bad teachers also did not help me understand this. I can do the math because I'm good enough at math, but I did not understand the chemistry behind the common ion effect. And so guys, honestly, when I went to teach this the first year that I taught AP, I was nervous. I was like, oh my gosh, I remember this kicking my butt in college. Or in high school. I never learned it in college. was a little unsure. But guys, the thing that was eye-opening was that when I finally sat down to teach this stuff, I found myself going, really? That's it? That's all there is to this? And guys, when I really sat down to chew on it deeply enough, because I needed to not only know it, I needed to teach it, I found that this is so amazingly, forgive me, it sounds weird, but it's beautiful. Because the chemistry behind this is so straightforward. If somebody could have just explained it to me well. So that's what we're going to do in the next 45 minutes is I'm going to explain this to you well. And then the thing that's cool is for the rest of this unit, we're just going to talk about different examples of contexts in which this common ion effect comes into play. And we're going to start titrating, and we're going to start problem solving. And all of chapter 7 spins on this idea. So we're going to figure it out today. You guys ready to go? Okay, so guys, in order to do this, and this is the thing that makes this so cool, you may want to write this stuff down with me. Guys, all the common ion effect is an interesting application of Le Chatelier's principle. So if you find it beneficial to write this down, knock yourselves out. If you don't, we're going to answer the question anyway. So guys, the question says this. Le Chatelier's principle. I don't even think I need to review that with you. But guys, Le Chatelier's principle allows us to answer questions like this. So Le Chatelier's principle says that increasing the concentration of a product will have what effect on the on an equilibrium system. So if we increase the concentration of a product, what's it going to do? So guys, what I'd like to do, and you could do this with me if you choose, but let's just do this. So we've got reactant 1, reactant 2, product 1, product 2. So if we increase the concentration of a product, what is that going to do to the equilibrium? Please. Yeah, well, we understand the predictor, right? Same side does the opposite side does the same. But how do we say it? Good, and we could do it that way, right? We could say shifts. And so shifts which way? Left to, are you guys okay with that? So increasing the concentration of a product shifts the equilibrium to the left. What are other ways that we could say that same thing? Okay. And so great. And so the concentration of reactants will go up, compensating for the stress. Go ahead, Brandon. And let's talk about that. And guys, I would propose to you that the best way to answer this question, and a lot of you got it quick, was the concept of shifting. So we would say that the reaction, the equilibrium shifts to the left, or you could say shifts towards the reactant side. Ethan, as you were adding, shifts towards the reactant side. But let's go with that concept of shifting. But now let's explain it. Because guys, the explanation, for you to understand the common ion effect, the explanation is also important. So why? Why does it shift to the left? Go ahead, Matt.
Because there's more of P1 and P2.
Okay.
You'll be able to collide with the other product.
Okay.
And that will facilitate the reverse reaction.
What happens, though, to the reverse reaction? There's one important term that you skipped over. Rate, right? Guys, can we sort of cluster around that idea that as we increase the product, right? As we increase the concentration of product, the collision between the product particles will increase, increasing the rate of the reverse reaction and shifting the equilibrium to the left. Does that make sense? Are you guys okay with all of that? Okay, so guys, with that said, we're going to use that as the foundation for how we're going to understand the common ion effect. So guys, we're going to say that it'll shift the equilibrium to the left, and that will shift the reaction towards the reactants, and we understand why. Increased product collisions increase the rate of the reverse reaction. You okay? Okay, so guys, with that said, let's now talk about the dissociation of acetic acid. So guys, when we talk about the dissociation of acetic acid, we now have an equilibrium system. And you don't need to necessarily write it down now, but guys, we're going to answer some questions about this. So applying the concepts that we established up here, let's answer this. Because guys, this is not just a retelling of the previous question. This is the critical bit that Kathin and my university teachers forgot to explain to me. Ready? So it goes like this. What effect would increasing the concentration of acetate ion have on the equilibrium? And what's the answer? No, but let's go back to what we did at the top of the notes. What effect will it have? Guys, you see in the connection, we said what? Increasing the concentration of the product, right? And you guys all had no problem saying increasing product, shifts it to the left, over here, da-da-da-da-da-da. Well, guys, what does that have to do with this? Well, here is an equilibrium reaction, and what is acetate? A product. Do you understand that you're answering the same question twice? So guys, the answer to this question is this. It shifts the equilibrium to the left. It's just a real example of the generic principle that we already established. Do you see the connections? Because now we've got a follow-up question. Two, actually. How could we do this? So guys, here is our beaker of oh, let's do this. You know what? Let's do that over. Guys, here's a beaker of vinegar, acetic acid. What's in there? Everything, right? We've got unprotonated acetic acid. How much? What was the number? Wasn't it like 99.3% or something like that? We got a lot of that. What else do we have in here? We've got acetate ion, and we've also got hydrogen. Now, guys, what do we know? Good heavens. What do we know about the relative amounts of acetate ion and hydrogen? They're the same, right? Because they come from the same place, this stuff breaking apart. What do we know about the amount of acetic acid compared to either one of these? A lot more, right? But guys, what do we also know about this? Just to make sure we're all really clear. Is there really any hydrogen ion in here? No, what is there? It's hydronium ion. We're just not going to choose to represent it. Is that okay? Okay, so guys, what we now have represented on the board in blue is this equilibrium. And what we said in the previous question was, let's increase the concentration of acetate ion. And you guys, same side does the opposite side does the same, shifts the equilibrium to left. You get to do all that, right, in your brain. But how do we do it in lab? Right, add CH3OH. How? There's no, guys, we can't go into the stock room and go, oh, look, there's the bottle of CH3COO. Say it again. We need a salt. Guys, we need a salt that contains the acetate ion. And we've got tons of those. So guys, the way that we do this practically in lab is we add a salt that contains the acetate ion. But that's the anion. Check this out. Why would sodium be a smart cation to choose to make sodium acetate? Good. Well, it dissociates, but guys, all acetate salts dissociate. All acetate salts are soluble. They're strong electrolytes. Why is sodium a better choice than aluminum acetate? It doesn't react with the water, right? Go back to what you learned 2 days ago. Sodium is the child of the strong base sodium hydroxide. Let's use the politically correct term. That makes sodium a negligible acid. Worthless, right? So guys, when we put this in water, the sodium doesn't do chemistry. it gets dissolved, but it doesn't react with the water. So guys, when we choose our salts to do this, we will always choose salts that have another ion that is negligible in terms of its acidity or basicity. So what does that give us? Well, it gives us lithium acetate, sodium acetate, potassium acetate, rubidium acetate, cesium acetate, calcium acetate, strontium acetate, barium acetate, right? Those are our choices, because those are the cations that form strong bases. But sodium acetate is the cheapest of all of those, so that's the one we're going to use. Get the idea? Okay, so what are we going to do? Well, we're going to go grab a bottle of sodium acetate, which looks actually a lot like table salt, and we're going to dump it in here. And when we dump it in here, now what do we have in solution? We've got sodium ion, because the sodium acetate dissolves and breaks apart into ions. But what else do we have? More of this. And as we add more of that, what does that do to the solution? And guys, specifically, and this, I don't think this is going to fit in my remaining space. Well, it might. Let me try, and if not, I'll just do it elsewhere. Guys, yeah, it's not going to fit. So let's do this. Guys, this is the question I want to ask you. When you add the sodium acetate, what happens to the pH of the... I want you to think. I love, Brandon, that you're ready to roll, but let's let people think. What does it do to the pH? What do you think? Is it going to go up or is it going to go down? Well, guys, let's take a look. So look at what we're doing. We are increasing the concentration of acetate ion, right? We've already established that that drives the equilibrium to the left. As it drives the equilibrium to the left, what is going to happen to the amount of hydrogen ion? It's going to go down, and therefore the pH goes. Get the idea? You get the idea? So guys, what you just learned is what is called the common ion effect. Why? Where does the name come from?
Because the sodium acetate has a common ion with the acetic acid.
Good. So guys, you may want to draw this. If you haven't been drawing with me up until now, you may want to draw this. Because this is the common ion effect in a nutshell. Because that's it. That is the common ion effect in a nutshell. And it goes like this. And maybe if you want to sort of label some of these pieces and parts. Guys, what we've got is a weak electrolyte. We have a substance that is weak. Therefore, it reaches equilibrium. And to that weak system that is at equilibrium, we are adding a salt. And that salt will be a strong electrolyte, meaning what? It'll fully dissociate, and its other ion will be, do I have to write negligible? I don't know how to spell it. All right, I'll try. Lig, L-I-G, ligeable. But guys, importantly, it will have an ion in common. So this ion is this ion, and it has an ion in common. Just a moment. So guys, once you've had a chance to get all this pulled together, I want to field questions. And then before we move on and start studying these systems mathematically, the important bridge that we need to talk about is, why do we care? But let's make sure we understand the thought before we talk about why we care about the thought. So are you all caught up? Because I know at least Matt has a question, but I want to make sure we all can engage in the questioning. Are you guys okay? Go ahead.
Yeah, the question and a comment. So the comment is, I mean, it kind of makes sense because what you're doing is adding a conjugate base, essentially.
Okay.
Even though it wasn't created the same way.
Mm-hmm.
And the equilibrium CH3COO
Uh-huh.
is a conjugate base.
Correct. That's right. And so, right. So can we, let's make that into a statement. So if our weak electrolyte is a weak acid, then the ion that we will be adding is the conjugate base ion. Similarly, if the weak electrolyte that we're playing with is a weak base, then the ion that we'll be adding will be its conjugate acid. Yeah, you're exactly right.
And then my question is, what if we were to add, like, instead of CH3COO minus,
Mm-hmm.
some other ion that could work as a base as well?
Hey. No, actually, she's not teaching, but she's over with Miss Call. Yeah, so do you know where her room is? Wonderful. Good to see you. Matt?
If we added more to that, would it have a similar effect?
No, it would not at all. It has to be a common ion. Yeah, it has. And the reason is because we're going to talk about in a minute, why do we care? And you're going to see in a second. So guys, other questions about the chemistry of this common ion effect or anything else? No?
So just saying, like, the common ion effect is just talking about matter. It's not like the effect that has. It just is when you add a solid.
Yeah, so let's sort of make it into, so what is the common ion effect? And the common ion effect is the change that takes place when you add a salt that has a common ion with a weak electrolyte. And the effect that you're creating is you're shifting that weak equilibrium to the left. Functionally, and guys, check this out. See if this makes sense to you. Functionally, what you're doing is you're making the weak electrolyte weaker. Guys, let that rattle around. If you heard that and didn't engage in that thought, that's important. See if this makes sense to you. When you add that common ion salt, what you're doing is making the weak electrolyte weaker. Do you see why that's true? Because what's happening to the amount of weak electrolyte that's broken apart when you add the sodium acetate? It goes down, right? You're creating more unprotonated acetic acid, meaning less acetic acid is broken apart, and you're functionally making the weak electrolyte weaker. Does your silence mean you understand, or you're so confused you don't even know, you're okay? Go ahead.
That's why they need to change the pH to whatever we want.
Yes, and we're going to talk about that in 2 days. And that's actually what we're going to do. Can we move on? Can I use that as a segue? Because guys, here's the deal. Brandon said, can we make this pH whatever we want? And the answer is absolutely. Why do we care? And guys, the answer is because this is a buffer. What you just built here is a buffer. And we're going to talk more about what that means in just a minute. But guys, understand these things, these systems called buffers are wildly important. Your blood is actually buffered by a sodium bicarbonate buffering system. And if it wasn't, we would all die right now. Like, there are so many systems inside your body that if the pH gets off just a little bit, you're done. With your blood, it's called acidosis, and it's a horrible way to die. But guys, there are so many systems in your body where if that pH changes even a little bit, it's game over. And the way that our bodies regulate pH is by creating these buffered systems in our bodies. This is not a buffering system that exists in our bodies, but guys, all buffered systems leverage this thing called the common ion effect. So the reason that we care about the common ion effect is because it's the chemistry of buffers. And that's where we're headed with this, is to understand buffers. And I don't expect you to understand what a buffer is yet, but understand we care about this because buffers are wildly important systems. So Brandon, what you're going to see in a couple days is we're going to talk about, okay, we're going to go do some chemistry in lab. And we want this chemistry to happen at pH 6.3. So how much of this do we need, and how much of that do we need, and how much water do we need to create a buffered system at pH 6.3? So that's exactly where this is headed, and it's fascinating chemistry. It's fun to teach. So guys, how you doing on the common ion effect? Go ahead, Daniel.
Is that why your body needs sodium and calcium? Is that the main reason?
Not exclusively. I mean, our bodies are such complicated systems that I can't, all right, I'm just going to record. Never mind, I'm going to get in trouble if I say it. Our bodies are such complicated systems that it just fascinates me that they work at all. Because the same ions that could participate in buffering are the ions that transmit neural impulses along our axons. So to say that's it is, no, it's other things, but it's that too. Yeah, it's crazy. So guys, where are you sitting with common ion effect? You okay? You realize that right now you're probably sitting there going, duh, right? All we've talked about is Le Chatelier's principle. Understand, guys, that if you're sitting there going, wait, this seems easy, this is the stuff that I couldn't figure out when I was 17, right? This is where second year chemistry fell apart for me in high school, because I didn't have anybody in my life to come and say, guys, it's really this simple. I know, right? But it really is this simple. It just took somebody to say, it really is this simple. So with the simplicity, or maybe the familiarity of the chemistry, because we've done so much with Le Chatelier's principle, now guys, we're going to dig into the details of this. So guys, here we go. This is called the common ion effect. I would claim to you that you don't need to write this down because you drew the picture. Because the picture was simply a representation of this sentence. The dissociation of a weak electrolyte, our acetic acid, is decreased by the adding to the solution a strong electrolyte, sodium acetate, that has an ion in common with the weak electrolyte. So if you want one neat, tidy little package that you can stick on your refrigerator, this is it. This is the common ion effect. But guys, I would propose to you that if you understand this, you understand way more than the sentence. But if you like the sentence, there's the sentence. You guys okay? Okay, so guys, here's what we're going to do. We're now going to start doing some problem solving. We are going to look at how this common ion effect weakens electrolytes. So guys, you're welcome to write this down if you want. Were you okay? Is that okay? Okay, so guys, we're going to do this. We're going to figure out the pH of a 0.3 molar acetic acid solution. Now guys, here's how we're going to do this. Well, all right, I'll just say it. Here's how it's an icebox problem, right? But guys, here's what I want you to do. No, not on this one. We're going to solve this together. So guys, it goes like this. CH3, COOH. Remember, we're going to make this big. Which one are we going to put first, the acetate ion or the hydrogen? Conjugate base first. You'll see why. Today is why. By the way, guys, I didn't include this, but the Ka for acetic acid is 1.8 times 10 to the negative fifth. We ready to go? Here we go. 0.3000 minus x plus x plus x. 0.30 minus x, x, and x. Ka is equal to acetate ion, hydrogen ion, acetic acid, x squared, 0.30 minus x is equal to 1. Oh, sorry, I shouldn't do that yet. So is approximately equal to x squared, 0.30, and we can then say that Ka is 1.8 times 10 to the negative fifth, and then solving this requires I find my calculator. So 1.8 times 10 to the negative fifth, multiply that by 0.3, take the square root, and I get x to be 0.00232 molar. pH is the negative log of hydrogen ion, is the negative log of 0.00232 molar. And so we go negative log, and the pH of this solution is 2.63. How'd I do? See? Oh, yeah. You guys good? You good? Okay. Oh, no, this is, unless I made a mistake, should be right. You okay? Now the game's changed. Guys, what we're going to do now is we are going to buffer. Sorry, we can't say that yet. We are going to change the equilibria that we previously studied by adding to this the common ion salt, sodium acetate. So the question now reads this way. What is the pH of a solution that is still 0.3 molar in acetic acid, but we have now added enough sodium acetate to drive the sodium acetate concentration up to also 0.3 molar? Now, guys, let's do this before we get into this. Just the 0.3 molar just the 0.3 molar acetic acid solution has a pH of 2.63. So what is the answer to this question going to be relative to 2.63? It'll be higher. Guys, think about this. Look at your balanced equation. If you look at this. So guys, here's what we're going to do. We are going to do the common ion effect. We are going to add acetate ion. When we add acetate ion, what direction does it drive the equilibrium? To the left. What happens to the amount of hydrogen? It goes down. As the amount of hydrogen goes down, the pH goes. Let's figure out how much it goes up. So guys, here we go. Same process. We've got CH3, COOH. We've got CH3COO. And we've got hydrogen. Now we're going to icebox this. Now, our concentration of acetic acid is still 0.30 molar. That's it. our initial concentration of acetate ion is no longer 0, because now we have another source of acetate ion right here. So our concentration of acetate ion initially is also 0.3 molar. This is 0. Now guys, this goes down by x, these go up by x. This then becomes 0.30 minus x, this becomes 0.30 plus x, and this becomes x. Guys, this is where this gets really fascinating. Check this out. Ka is equal to, and guys, let me just tell you, if on the previous problem solving process you did not do this with me, that was probably okay because you knew how it was going to play out. You got to do this one with me, guys. This, I'm about to show you something you got to know. So here we go. CH3COO, sorry, that's a C. OO minus, H plus. Okay, so I'm going to rewrite this. 1.8 times 10 to the negative fifth is equal to 0.30 plus x times x, Daniel, just a minute, and 0.30 minus x. Are we okay? Okay. Now, guys, do this with me. Are you all caught up? Okay, go back here. What allowed us to do this, and what did we do? We got rid of the minus x, and it's because of the Ka value, but what was the logic behind us getting rid of the minus x? It's insignificant compared to what? The initial concentration. Guys, watch, this is important. This x represents the amount of acetic acid that falls apart. And relative to 0.3 molar, it's a rounding error. But guys, watch this. Notice how this is different. We still have our 0.3 minus x. But look at what else we've got. A 0.3 plus x. Now guys, does it seem reasonable that this x is so small compared to 0.3 molar here, we could disregard it? Could we also then disregard it because it's also small compared to that 0.30? Absolutely. So guys, what we do then is we say this is approximately equal to this. We get rid of the plus x and the minus x. But now what happens? The 0.30s cancel. Guys, don't look away. Don't look away. The 0.30s cancel. What does that then mean? It means we're left with x. But now we've got x is equal to what? 1.8 times 10 to the negative fifth, which is what? Ka. So guys, here's the trick. When you build your buffers, if the concentration of your weak electrolyte and the concentration of your conjugate base salt are the same, your hydrogen ion concentration is Ka. You think you should write that down? Me too. Just write it down. Just a minute, Ethan. So guys, let's say it again. When you build your buffers, and I'm going to say it this way, see if this makes sense. When you build your buffers, if you build them with equal molarities, that means the concentration of the weak electrolyte and the concentration of the conjugate salt. If those molarities are the same, then your hydrogen ion concentration is Ka. But now guys, watch this. You ready? We're not done with the problem, right? We want to know the pH. pH is equal to the negative log of hydrogen ion is equal to the negative log of 1.8 times 10 to the negative fifth is equal to 4.74. So, right, we got some stuff to talk about, right? So first of all, did this system do what we expected it to? Our previous pH was 2.63. We thought that adding the conjugate ion would shift the equilibrium to the left, decreasing the concentration of hydrogen and increasing the pH. And we found that it did. But guys, let's put this in context. Our unaffected pH, if you remember, was 2.63. So how many times less acidic is this? 100. Using round numbers, it's 100 times less acidic. Because remember, guys, these are logarithmic relationships. They are exponents of 10. So 2 powers of 10 is 100. So guys, this system that we created is 100 times less acidic than the system that we didn't add the salt to. Just a second. Oh, you're just stretching? Okay. So guys, does that make sense? Now let me share something with you that I think you're going to find useful. You all wrote down this sentence, right? That said that was relative to this, and we had something magic happened. And we said that if our molarities are the same, right? Oops. If our molarities are the same, then the concentration of hydrogen is what? Ka. But now, guys, are you okay with that idea? But now, guys, watch this. Look at what we then did. pH is the negative log of hydrogen ion. But, guys, if our molarities are equal, what is the concentration of hydrogen ion? Ka. And what do we call it whenever we take the negative log of something? It's pKa. So guys, it goes like this. You're going to want to scratch this down with me. If molarity of the weak electrolyte is equal to, you know what, I can do that differently. Just a second. Because the brackets mean molarity. So if, let's do it this way. If the molarity of the weak electrolyte equals the molarity of the salt, then pH is equal to pKa. pH is pKa. If the concentration of the weak electrolyte is equal to the concentration of the salt, then pH is pKa. Now guys, why do we care? We care because of what Brandon said. He said, wait, can we make this pH anything that we want? Yeah. But guys, it gets even better than that. Because what we can do is this. If we grab a pKa table, which exists, imagine that we go into lab and we're like, we want to buffer at pH 5. What do? Well, we grab a pKa table and we find a weak acid with a pKa of 5. And then what do? Well, we go grab the bottle of that weak acid, we go find a salt that shares an ion in common, create a solution where the molarities are the same, and we just made pH 5. Can we say that again? Because this is stuff you're going to do in lab. So guys, in order to build these buffers, we're going to be smart about this and say that the requirement is that we make a buffer at pH 5. To simplify that, what we're going to do is we're going to find a pKa table. And we're going to find a weak acid that has a pKa of 5. Once we find that weak acid with a pKa of 5, all we have to do is take that weak acid, take a salt that shares an ion in common with it, the conjugate base ion, and we make an equal molar solution of that, and that thing is guaranteed to be pH 5, and we're good. But that only works because of all of this math. Because when the molarities are the same, they cancel. The hydrogen ion concentration is Ka, so the pH is pKa. You get the idea? So questions. I know I've been ignoring some, but let's do them now if you're ready. Go ahead.
We saw this on the AP test. But we saw
Not if, when, but keep going. Yeah.
yeah. So if we saw an example like this on the AP test,
Mhm.
would we have to write out all the math still, or could we just write pH equals
It depends on the situation. If the question were written like this, you would have to write out the icebox. Frankly, and I should say this, you're going to see in chapter 17, there is an equation called the Henderson-Hasselbalch equation. And the Henderson-Hasselbalch equation is it's a quick and dirty equation that allows you to figure out the pH of buffers. And functionally what it does is it just takes this math and all these wonderful cancellations and just puts it in a really tight equation. They took Henderson-Hasselbalch away from us with the 2014 revision of the test, meaning that they always demand iceboxes. Yeah. So if you saw it in multiple choice, then they're wanting you to know pH is pKa. If you see it in free response, they're requiring the complete solution. You guys good? You ready to talk buffers? You guys are going to love this chemistry. Ready? So here we go. Guys, we are going to call this solution 1. Okay? This is acetic acid without the salt. We're going to call this solution 2. This is the acetic acid with the common ion salt. Good? Okay, so here you go. This second solution is a buffer. And we're going to talk about what this means right now. But before we do, there's one more thing we've got to include. Guys, I don't know if you've already written this down. But guys, remember, you already wrote this down, right? Don't write it again. If you have equal molar amounts of acid in conjugate base, the pH is pKa. You're good? Okay. So guys, let's talk about buffers. So let me define it for you, and then we're going to play with the chemistry. So guys, by definition, a buffer, I'm going to say it in the singular, it's written in the plural. A buffer is a system that resists changes in pH. Again, a buffer is, or buffers are, systems that resist changes in pH. So you create a buffer and you dump hydrochloric acid in it and the pH doesn't change. It's magic. The first time you see it, it's magic. But guys, you take a buffer and you dump HCl in there and the pH doesn't change. But the thing that's really cool is you take that same buffer and dump sodium hydroxide in it and the pH still doesn't change. It's really cool. So how do these things work? Well, guys, fundamentally, they are combinations of a weak acid or base and a conjugate salt. Gosh, that sounds familiar. Sounds like the common ion effect. That's the point. So, guys, the question then becomes, how do they do this? And guys, fundamentally what buffers do is this. They have this really amazing ability to soak up hydrogen ions and to soak up hydroxide ions without significantly changing their pH. So guys, how do they do it? You ready to figure out how? Because this is actually really cool. Can we talk about how? Okay, so guys, let's go back to our acetic acid system. Do this. Write it big. Oh, and hold on. When I say write it big, leave yourself at least 3 spaces above this and make it the width of your paper. Guys, what I'm about to teach you when you get to college will make you the hero of whatever study groups you join while you're taking freshman chemistry. Don't give this stuff away for free. At least apple fritters, potentially a first date. Okay? Seriously, don't give this stuff, this is worth something. So guys, how do buffers work? Well, this is how buffers work. Let's talk about the chemistry of these magic systems that can just absorb hydrogens or OHs, and that's important. It's or OHs. So guys, but first of all, let's make sure we understand the definition of a buffer. So we get, from what we've talked about already, that if we have a buffer and if we dump in hydrogens, what happens to pH? Nothing. Or if we dump in OHs, what happens to pH? Nothing. So guys, that's what makes buffers magic, is we add acid, pH doesn't change. We add base, pH doesn't change. But for you to understand this, you've got to be able to look at pH and watch it not change. So where on the board is pH? It's blue. That's why I made it blue. So guys, you want to do this with me. This is pH. So guys, if pH doesn't change, the blue guy had better not change. Because if it does, it ain't a buffer. Okay? Now, what can buffers absorb? Well, the answer is hydrogen ions and hydroxide ions. So let's do hydrogen ions first. Where do we get good sources of hydrogen ions? Strong acids. HCl, HBr, HI, HC, you get the idea. So guys, I'm not going to represent the whole thing. I'm going to give you the H, but not the Cl. Why do we care about the Cl? Doesn't do chemistry because it's the child of O. I'm going to give you the H. Do it with me like this. So now you're going, wait a minute. Liar? You told me that buffers don't change pH, but I just added H's. And if I'm adding H's, that makes H go up. And I'm watching H, and H just went up, and this ain't a buffer. Because guys, watch what happens. When you add these hydrogen ions do, and you understand those hydrogens are really attached to hydronium ion, right? But we don't care. But guys, understand, these hydrogen ions don't get left alone. Can you picture this? Can you picture that what we're talking about is a beaker, and inside this beaker, we've got acetate, we've got acetic acid, we've got acetate ions, we've got hydrogen ions, and we just dumped in a bunch of HCl, right? But guys, here's the thing that's cool. When you dump in HCl, which is a source of hydrogen ion, those hydrogen ions don't get left alone. The ions and the substance, the particles that are already in solution, don't go, oh look, hydrogen ions, gosh, that's neat. Let's just let them go be hydrogen ions. Guys, what happens is acetate ion goes, oh no you don't. You're not welcome here. And I'm going to tie you up and I'm going to turn you into acetic acid. You don't get to come in here and just cause problems. This acetate ion goes, I got this. And that acetate ion goes, hey, yo, I'm going to grab a hold of those hydrogen ions and I'm going to turn those extra hydrogen ions into unprotonated acetic acid ions. And what happened to this? Nothing. Isn't that cool?
Is that what we talk about on ingredients?
No. But now, guys, you're like, well, yeah, okay, that makes sense. I got that. But now let's reset the clock. Pretend that we never added acid, HCl, to this buffer. Now let's add some base. Where are we going to get a bunch of OH? Sodium hydroxide. We don't care about the sodium though, right? Why? Doesn't do chemistry. Now we add this OH. Because this is cool. Watch this. We're reset to 0, right? We never added any acid. Now we got this. We got our bucket of stuff. And now instead of HCl, we're going to add NaOH. And the NaOH goes into solution, and what does the Na do? Nothing. But what does the OH do? That OH is not welcome. But guys, this buffer's got an answer. Because this buffer goes, hey guys, I got this. But it's no longer the acetate ion that's got this. The acetic acid goes, I got this. You are not welcome here, hydroxide. I got it. And I'm going to grab a hold of you, and I'm going to take you, and I'm going to sacrifice myself. I'm going to give the OH a hydrogen. And when the acetic acid gives an OH the hydrogen, what does that make? Water and acetate ion. And what happened to the concentration of hydrogen ion? Nothing. Guys, that's what makes buffers such amazing systems, is buffers have got an answer to both problems. If you dump an acid in a buffer, the conjugate base goes, I got this. But if you dump a base into a buffer, the unprotonated acid goes, I got this. But then you're like, wait, if the unprotonated acid gives away a hydrogen, doesn't that make hydrogen ion go out? No, because where does the hydrogen go? To water. And it doesn't mess with the pH. You get the idea? Isn't that cool? But now guys, watch this. You're going, yeah, that's pretty neat chemistry, but I don't think I can do this. No, I can't. I'm going to have to do this. Okay, I think I have an answer. Go here, and then guys, is that okay? Okay. All right, so here we go, guys. Go on your notes with me. This is solution number one. Go to solution number one. You with me on solution number one? Here's what we're going to do. And if you don't want to muck up your notes, maybe you just watch me. Check this out. Just watch me. I'm going to dump some base into this solution. How does this solution respond? Acetic acid goes, I got this. I got you. We're okay. I got you. Acetic acid goes, yo, and it turns into this, and it gives away water, and this doesn't change. But guys, check this out. What if we add hydrochloric acid? What happens? There's no defense. Because guys, how much acetate ion do we have? Functionally none, right? We've got this molarity of acetate ion. That's nothing. That's shot in a moment, and then all of this extra hydrogen ion goes, woohoo! Here we go. pH falls through the floor. Guys, this is not a buffer. Yes, this system can deal with hydroxide, but it doesn't have any acetate ion to deal with hydrogen. This is not a buffer. What about this? Do you see the difference? Because now, guys, what if we add hydroxide? We still have 0.3 molar about acetic acid. Hey, guys, no problem. I got this. Hydroxide? Got it. We're going to take this. We're going to take this. We're going to make it into water. pH doesn't change. But now, guys, look at the difference that adding the salt made. Adding the salt gives us a huge reserve of acetate ion. So now, when we dump in HCl and we got all these hydrogen ions floating around, now all of this extra acetate ion is present to go, I got this. I got it. We're good. I'm going to just do this. I'm going to make some more acetic acid. No problem. I got this. Now, guys, does this go on forever? When does this end? When we run out. And guys, how much do we have before we run out? 0.3 molar. And that's a lot, but it's not infinite. And you're going to find out next time we call that the capacity of the buffer. The more of these, the more concentrated these ions are, the greater the capacity of the buffer. This doesn't go on forever. And we're going to talk next time about when buffers fail. And when do buffers fail? When they run out of the things that are doing the chemistry. But guys, up until that point, these things are amazing at absorbing ions. Do you see how the chemistry works? Because those are buffers, yeah.
So with the buffers, you have 0.3 molar of that.
Well, you need to remember, because we don't know what you're talking about. Acetate ion or acetic acid? Okay, so this stuff. Okay, keep going.
So when you're looking at how much it has in reserve, you look at the initial amount and subsequently look at the final amount.
Why is it appropriate to look at the initial amount? What did we do right here? Got rid of the x's, right? That's why. Because do we really have this much? No, we have a little more. Do we really have this much? No, we have a little less. But given the initial concentrations, the little more and the little less are so insignificant that we can get rid of them. So functionally, we think of them as being that. Good. So what if your Ka is greater than 10 to the negative third? Those make lousy buffers. Really, the smaller the Ka value, think about this. The smaller the Ka value is, the better the buffer will be, because the amount of substance that you gain and lose because of dissociation is smaller. So so you would seldom would you build a buffer with a weak acid that has a Ka in the order of 10 to the third, because so much of that. Think about it. So much of this would break apart that if you added a base to it, that buffer would fail really quickly. Does that make sense? If it does, that's really cool, because that was a deep thought. But that's the idea. You want to build buffers out of weak electrolytes that have low Kas or Kbs, because those are more stable. They have greater buffering capacities because they lose less ion to dissociation. That's a neat thought. Guys, what do you think? Crazy, right? So let me ask you this. Do you understand now why I told you when you write out your ice boxes to put the conjugate base ion first? It allows you to represent this chemistry. This is good stuff. So, guys, we're done. Now,
When we get it
do what?
buffers.
Well, so here's the thing. Here's our homework. So guys, the question on the table is, when do we get to start doing this? And the answer is, what you're going to find, Brandon, is that the lecture and the lab are going to get out of step, because we've got to help you figure out how to titrate well before we can start titrating buffers. We're going to do it mathematically first, and we'll do it physically later. So guys, this is your homework. We are going to break at the class break, and then we're going to get together during lab, and we're going to sort of talk about what the coming weeks looks like. So let me finish recording really quickly, and then I'd love to. Uh-oh.